Hey guys, welcome to your mass spectrometry notes. Let's talk about mass spectrometry. So what you're looking at right now is a part of your notes. Try and follow along as I go through your notes. Also, I add in a picture here of a mass spectrometer. So you can see the sample enters here. You put your sample, whatever you want to analyze in here, it gets heated up and vaporized, and then it gets pushed through the machine. This electron beam source actually makes your sample into an ion. You'll learn what an ion is later. Basically, it is just an atom with an electron or two or three removed, and that pulls your atoms towards this magnet. Atoms work a certain way. I should say ions. Once they become ions, they work a certain way in a magnet where they pull based on their charge different ways, and so different atoms will be separated. So they bend a little bit in their path and they hit the detector plate. The detector plate is the one that is able to analyze the atom and determine the atomic weight of the particle. You can see the low mass particles show up on this side of the plate, and the high mass particles show up on this side of the plate, and that's how we are able to use a mass spectrometer. So this method of mass spectrometry is used to measure the mass of atoms, compared to the carbon-12 standard. If you've done your atomic weight notes already, you know that we use the atom of carbon that has 6 protons and 6 neutrons, giving us carbon-12, a weight of 12, as a standard. We call that as having a weight of 12.00 atomic mass units. So like I said, they pass a sample of atoms through the mass spectrometer. It superheats the sample, turns them into positive ions by removing some electrons, and shoots them through a magnetic field where they hit this detector plate. They can measure the amount of individual different isotopes or nuclides, we can call them nuclides as well, in the sample that are deflected in order to compare their masses. So we can see the mass of every different isotope in the sample. Also, mass spectrometry can be used to measure how abundant each isotope is in a sample. Abundant meaning how much of that isotope is present in a sample. So on the right here, follow along in your notes. This bar graph shows the mass spectrum of magnesium. So we took a sample of magnesium and put it in the mass spectrometer. You can see that we get this one giant, not giant, but relatively large peak that corresponds to a 78.70% abundance. That means 78.70% of the atoms in this sample of magnesium weigh about 24 atomic mass units, whereas we have 10.13% of the atoms of magnesium that weigh 25 atomic mass units, and 11.17% that weigh 6 atomic mass units, right? So this mass spectrum is just a plot of intensity or abundance. How much of this type of isotope, this particular isotope that weighs this much, is present in the sample. The higher the peak, the more of that particular isotope is present. Then in this table in your notes, you can see that we have written down the 3 isotopes corresponding to those 3 peaks, right? One peak weighed 24 atomic mass units, one peak weighed 25 atomic mass units, and one peak had 26 mass units. So we put these in this table for each isotope shown in the mass spectrometer, and here are their corresponding weights as given by the mass spectrometer. So go ahead and take a moment and find all in our sample of magnesium here. You can see all our magnesium atoms. Go ahead, pause the video, and color code all of your isotope 24 magnesium atoms. All right, did you find them all? You can see that they are present in the highest abundance, which makes sense because that peak corresponded to about 78%. Now let's do the same thing with our magnesium 25 isotope. All the isotopes that correspond to magnesium 25. There you go. You should have gotten all your magnesium 25 atoms, a much lower percentage, right? Closer to 10.17%. And now do the same thing for your magnesium 26 isotopes. Did you find them all? So again, a smaller abundance, smaller percentage, smaller peak of your magnesium 26 isotopes. So what we want to do from all this information is take our mass spectrum and be able to calculate the atomic weight, or we can also call it the average atomic mass of magnesium. How are we going to do that? Well, we are going to use this formula. We are going to take the percent abundance of magnesium 24 and multiply it by the mass of magnesium 24. So we're going to look at our mass spectrum for the percent abundance of magnesium 24, and we're going to look at our table that gave us the mass of magnesium 24. And then we're going to multiply them together, and then we will add in the percent abundance of magnesium 25 times the mass in our table of magnesium 25, and then we'll add in the percent abundance of magnesium 26 and the mass of magnesium 26. In this way, we've got all our masses represented, but we're also going to take into account how many of the isotopes are present in each sample. So we'll get a really good representative atomic weight, average atomic weight of the magnesium isotopes that are present in nature. All right, so first let's start with our percent abundance. We know that the peak in our mass spectrum gave us a percent abundance of 78.70 for magnesium 24. Notice I color-coded all these guys. The percent abundance of magnesium 25 was 10.13%, and then our percent abundance of magnesium 26 was 11.17%. I got all of these percentages from the mass spectrum, looking at how big the peak was, which shows us the percent abundance of each of these three isotopes, right? Isotopes are the same element, but they all have different weights. And then I can use my table to substitute in the actual weights, the actual mass of each of my isotopes as well. So the weight of magnesium 24 is 23.9850 atomic mass units. The mass of magnesium 25 is 24.9858 atomic mass units, and then magnesium 26, 25.926 atomic mass units. So plug that all into your calculator, use your parentheses, add up all your values, and then of course round your answer to 2 decimal points, and you will end up with 24.31 atomic mass units. That is what we call the average atomic mass for magnesium. We're able to take into account the 3 different isotopes of magnesium that are present in nature. All right, we'll do a lot more practice coming up. Thanks. Oh, sorry. One last thing that I wanted to point out. When we take a look at our when we take a look at all of our different isotopes and what is isolated in our sample, you can see that we've represented how much of each isotope is present, and we've multiplied that by the actual weight of the sample. So our average atomic mass is able to represent all of the isotopes in a sample and give us a really good representation of what the average atomic mass is. Okay, we'll do a lot more practicing with these problems. Okay, thanks very much. See you in class.